Welcome. Today is finally the day we are going to start the Railgun build. This won't be your average two-part build where you chuck on some capacitors onto a set of conductors and shove a projectile through it. No, this is going to be a high-level research series. I will be going according to true engineering procedure and test designs to achieve the best railgun today. However, in order to do that, we must ask ourselves the questions how and what every time we think of something. For now, we'll just ask ourselves the most fundamental questions for this project. What is a railgun and how does it work? In this build we will add some more in-depth knowledge as we go through the process, but for now we'll stick to the basic operating principle. So, what is a railgun? A railgun is actually a homopolar linear motor. It has two parallel conductive rails connected to a power source. Usually it is an open circuit, but when an armature or projectile is inserted between the rails, there will be a flow of current. Any conductor with a flowing current will produce a magnetic field. The strength of the magnetic field in a wire can be described by the Biot-Savart law, which is far more complex in nature since it's applicable in non-straight wires as well. But we'll keep it simple and we'll focus on the straight wire instead. This law gives us the formula B equals mu naught times I divided by 2 pi rho, where B is the magnetic field strength in Teslas, mu naught is the permeability of free space, I is the current in amperes, and rho is the distance to a point on the magnetic field lines. As we can see from this formula, is when I goes up, B goes up. But we can also see if rho goes down, B also goes up. But in many cases, rho is usually a constant, and the magnetic field strength will be proportional to the current. The combination of this magnetic field and the current being conducted by the armature will produce something called the Lorentz force, or its manifestation as the Laplace force. This force is named by the Dutch physicist Hendrik Antoon Lorentz. He is known for the Lorentz transformation written in 1887, which laid the foundation of the theory of special relativity, later written by Einstein in 1905. Now his days of glory aren't over, because he will now lay the foundation of this project, even though he probably wasn't the first to have derived the Lorentz force. Physicists probably only care about the Lorentz force when they have a charged particle in an electric field, so they can build their fancy particle accelerators. I've done quite some theory on nuclear particle physics as a high school paper, but perhaps in another project. One involving disintegrating ordinary matter with antimatter, maybe? For now, we don't care about this kind of useless Lorentz force, and we will focus on its other derivation. The Lorentz force we do care about states that F equals I times L cross B, where F is the force of the projectile accelerated between the rails, I is the current, L is the length of the conductor rails, and B is the magnetic field strength in Teslas. Now, what does this cross-product garbage mean? Since we are working in three-dimensional space and we want to know what direction our projectile is going, we need to represent our parameters as vectors. If we take the cross product of two vectors A and B and put them in a vector matrix, we will get the scalar of A times the scalar of B times the sine of theta and a direction vector, and will produce a vector C. As we can see here, when A and B are perpendicular in 90 degrees, it will create a a perpendicular vector c. But as we can see here, when theta is 0, there will be no vector c. So how can this theory be applied to our case? Well, we take I cross B and we put it in its matrix, and we can use this standard coordination system, and here we can see what's happening in a railgun. So as we can see, I moves in the negative y direction and B goes up in the positive z direction. So we can already see what's going on here. There is no magnetic field right there, and there is no current going this way. So we only have these two. And how does this work? Well, what I forgot to tell you was that the I vectors correspond to the x axis, j corresponds to y, and the k vector corresponds to the z axis. So if we try to solve this matrix, we will get this submatrix, this one, and this one, because I, to get the I value, we have to cross out I, because the vector times itself will just be 0. There will be no cross product. So we just fill that in here, we do this, fill it in here, and we fill it in there. So what we'll eventually get is x was 0, yz is 0, bx is 0, and bz is present, yx is 0, yy is present, bx is 0, by is 0. But as we take its cross product, we can see 0 times 0 minus 0 times 1 is just 0. Same here, 0. And as we can see, is that our IY, BZ, which came in right here, they get multiplied by each other. So we'll get IY times BZ times I. But as we saw, I moves in the negative y direction, so we must not forget this one. What this gets us is B times I. But where does it go? It goes in the I direction, in the negative I direction. So that's this way. And what does this give us? It gives us the force right here. And this completes the proof of what happens right here. Usually this is simplified by just using the left hand rule, where this is the magnetic field, this is the current, and this is the force. So as we can see, is our magnetic field goes in the palm of our hands, the current moves that way, so the force goes this way. Now that we know more about linear algebra and its applications and know what direction our projectile will be going, let us focus on the scalars or values of these vectors. As we have seen before, is that B is proportional to I, the current. But now we have seen that F is proportional to B and I. Therefore, a high current is extremely important for a good design. So, if if we take a look at the formula and we integrate it into each other, we will see that mu naught is a constant, L is a constant, and the rho is a constant. So what we'll see here is that F is proportional to I squared. So to get the best design, we will have to get a high as possible current, and in the next video we will discuss how we will approach our design. But as many have guessed, we will be using capacitors to get the highest possible current. Of course, there's a lot more theory to this, and I haven't explained it in the best way that was possible because I wanted to keep it pretty short before you fall asleep. I hope you haven't fallen asleep. But in the next video we'll talk about how we are going to approach the design, and we'll talk about some flaws, some problems, and how we are going to deal with them. So I hope I'll see you next time.